one thing we noticed is that, so basically what we noticed is that there's a connection between combinatorial solvers, like Dijkstra, maximum spanning tree algorithms, top K, and so on, and exponential family distributions. And in particular, solving a combinatorial search problem in this form, so this is what solve does. Solving this problem is equivalent to doing two things. Basically, solving this problem is equivalent to first defining an exponential family distribution over all the possible solutions. So basically, starting from this, you can define, so for example, assume this is the top K function, and Z is a K hot vector. Basically, this is equivalent to first defining an exponential family distribution over all the possible solutions. So basically, we have an exponential family distribution over all the possible K hot vectors, where the probability of a solution is proportional to the score of the of the solution here. So basically, the higher the score of a solution, the higher the probability of that solution in this distribution. And then after you define this distribution over the solutions, you just get the most likely solution. Basically, defining a distribution over the solutions and then just picking the most likely solution is equivalent to just calling the combinatorial solver, like an API. And finding the most likely solution to the combinatorial solver is basically we return the solution with the highest probability, and this is called maximum a posteriori inference, or MAP. Here, MAP basically is equivalent to calling the solve function that, given the input weights theta, gives you the solution Z to the problem. And one thing I want to emphasize is that basically we don't really need to construct this exponential family distribution over all the possible solutions explicitly, because it costs a lot. We don't want to do that. It's enough to know that this distribution exists, because constructing P, like this distribution explicitly, basically requires us to enumerate all the possible solutions. So for example, all the possible paths from A to B, or all the possible K hot vectors, that in many, many cases it's not really feasible. It can be very, very costly, and we don't want to do that. Is it clear so far?
So you said you don't define the distribution explicitly. So how do you actually define the hyperparameters for your distribution?
What do you mean?
So how do you choose the sort of parameters for the expression?
So here, the only parameter is theta, and theta is basically the input to the solver. Okay. And it's something we want to learn, basically. So there are no hyperparameters, pretty much. Okay, thanks. There are hyperparameters, but they are coming up like next slide or something. So like, but basically, long story short, we have an algorithm that gets an input and gives you a solution. We want to backpropagate through this algorithm. And one way we can do that is by noting that calling this algorithm is equivalent to defining a distribution over the solutions, and then just picking the most likely solution. And it's enough to know that this distribution exists, basically.